Yeah, so we're looking at these two small molecules, comparing which is more acidic or not. I already went over with people in the class, the little bit of review from last class. And we've determined, based on this increased number of oxygens attached to our carbon, that it is A that is more acidic. This A group, this is a carboxylic acid functional group, and in B, we've got an alcohol group. And carboxylic acids are also more acidic than alcohols. But that's, in the future. We have now a third, I think this is our third, definition of an acid. So we also have the Lewis definition. We had Arrhenius, and we've also had Bronsted-Lowry. And now we're learning yet another acid-base model. So the Lewis model focuses on the transfer of an electron pair. So an acid accepts an electron pair, it's these 2 points, and our base is an electron pair donor. So in our Bronsted-Lowry model, we're focused on the proton, the H+. We're focused on our proton, and in Lewis, we're focused on the electron. So the directions are opposite. In the Bronsted-Lowry model, if we're donating a proton, then that makes it an acid. In the Lewis model, if we're donating an electron pair, the thing we care about, then we're a base. In both cases, H+ behaves like an acid. So our Lewis model, focusing on the electron pair, helps expand our definition of things that are acids and bases. So in this example of ammonia, NH3 and an H+, the ammonia can donate that pair of electrons to reel in this proton that's floating around in solution as a hydronium ion. And then when we draw those two things together in the Lewis model, we put 2 dots between them rather than lumping it in with the rest of these hydrogens. So again, our Lewis definition expands what we can consider acids. Our Lewis acids don't even need to contain hydrogen. So that's one way that the Lewis system is helpful for us. For example, we could have boron trifluoride and ammonia. And you may remember from Lewis structures, that boron is happy with just 3 bonds. And it's not going to have any lone pairs on it either. So boron has an empty orbital. It's only got 6 electrons around it, and that leaves an empty space for a pair of electrons to get donated. And since boron trifluoride, the boron here, is accepting that electron pair, it's behaving like an acid. And our ammonia, which we know is a weak base in our Bronsted-Lowry model, since it's donating those electrons, is a base, a Lewis base. And then when those two things go together, we call that an adduct. The definition, or where that came from online, was Latin, I think, adductus, or like to bring in, draw in, or portmanteau, combining the two words, addition and product. So just smushing them together. And this is called, what is it? a dative bond, which you don't need to know, but I believe that's what that's called. So it's not a full covalent bond. They're not actually establishing a covalent bond relationship. And it's also not the same as an ionic bond where it's a positive negative charge thing. It's some secret third thing that we won't talk about very much. More important information, our Lewis acid has an empty orbital, or it can rearrange electrons. We'll see examples of that that can accept an electron pair. So when ammonia donates those electrons, we maybe get something like that, where that empty orbital interacts with that lone pair, and we get our addition product or our adduct. And Lewis acids are nice for a couple of things. We're mainly going to be looking at aluminum and boron. I don't even think we have any examples left in the slides. But aluminum being right next to, right below boron on the periodic table. Boron and aluminum both form 3 bonds. With 1 empty orbital remaining. You may remember that from 1A or 3A. And since boron and aluminum form 3 bonds with 1 empty orbital, they have an empty orbital, meaning that they can form adducts. They can act as Lewis acids. And accept an electron pair from something that has extra electrons. So boron and aluminum are 2 main group elements that you should identify as things that can act as Lewis acids. So boron and aluminum with 3 bonds can act as Lewis acids. Those are, of course, not the only things that can act as Lewis acids. Molecules can also act as Lewis acids. So for example, water can attack or donate an electron pair to carbon that's in CO2. And CO2 can rearrange some of its bonds. It's got double bonds, and oxygen is more electronegative than carbon, and so oxygen can at least temporarily take on some extra electrons. If this double bond moves to a single bond, oxygen will be a little bit overloaded. Our carbon is going to have room for another pair of electrons, and so it can bond with water. And then at the same time, or right after that at least, the oxygen that has extra electrons can attack one of those hydrogens in the water molecule, and then it reforms to carbonic acid. So double and triple bonds. Can shift electrons to the more electronegative, I'll just do En, elements. I don't expect to ask a question where you have to figure that out, or like show how those electrons move around, because that's kind of organic chemistry stuff. This will be helpful if you have to take organic chemistry. You're going to be doing a lot of this stuff. So we're taking a peek at it now. And when carbon dioxide dissolves in water, it does actually form carbonic acid. It can also go the opposite direction, go back. Where I think that the Lewis definition is really helpful is we looked at small, highly charged metal ions. And we talked about how those can make solutions acidic. And the reason that those can make solutions acidic is because they form adducts with water. So Al3 plus or Fe3 plus or maybe Sc3 plus, scandium 3 plus, those sorts of things, small and highly charged metal ions can form adducts with a bunch of water molecules. So they're accepting these electrons and forming those dative bonds that we were talking about earlier, those they're just kind of stuck together bonds to form this big hydrate complex. And you don't need to worry about the stoichiometry here, really. For small things, it's usually either 4 waters or 6 waters. And the reason for that is just spacing. So when we talked about dissolving things, or hopefully you've heard about dissolving things, right? Our water molecules are coming and tearing things apart, and then we've got ions that are floating around with a bunch of water molecules around them. And since aluminum has a 3 positive charge, the oxygen is the more electronegative part of our water molecule, our polar water molecule. And so the negative part, the oxygen part, is going to cozy up to the aluminum. And just because of space constraints, we can only fit probably 6 of them around the aluminum. And the partial negative charge of the oxygen sitting next to the positively charged aluminum helps to stabilize some of the charge and keep it in solution. So it's 6 because of space constraints. It's not big enough that you can fit 8 or 12 or 7, what have you. So those would be experimentally determined. But this is the reason why our cations, our small positively charged metal ions, can form acidic solutions. Questions so far? All right, that's most of the important material. We'll just talk about acid rain a little bit. So some fossil fuels, things from dinosaurs, thank you dinosaurs, very cool, especially coal, contain small amounts of sulfur impurities, and during combustion those can form sulfur dioxide. And sulfur dioxide is a common air pollutant. They can also form NO2, nitrogen dioxide, which I think is brown, or can form a brown haze. Anyway, those are 2 common air pollutants produced when you combust fossil fuels. And the reaction of those, so we've got our SO2, we've got our NO2, reacting those with oxygen and water, which are going to be in the air. The water probably one of the products of our combustion reaction. Those things can form sulfuric acid and nitric acid in the air. So SO2 forms sulfuric acid, NO2 forms nitric acid in the air. So just probably right now even, there's some of that stuff floating around thousands, hundreds of feet above us. And those acids can combine with rain, especially if the concentration of those gases is high enough. Some of that will get caught up in the rain. And this problem is worse in the Northeast because the natural air currents are going to bring those combustion products from coal that float out there from the Midwest. And because of those 2 things, because of these forming these acids in air. Rain gets kind of turbocharged sometimes in terms of its acidity. It's naturally going to form carbonic acid in the atmosphere. We looked at the way that that forms earlier. And so rain that has a saturated CO2 level is going to have a pH of 5.6. It's already going to be a little bit acidic. That's not really enough that we would have to worry about it too much. But if you have nitric and sulfuric acids mixed in there, the pH can fall below 4.3, and that's when it starts to become a little more dangerous. Not really for us, like unless you're out in it a lot, but more for metals and carbonates and stone and other things. So like this statue that's been worn away because of acid rain. So that's like cement in statues, bridges, railroads, cars. It's all really bad for that stuff. And it's especially bad also for lakes and rivers because they're going to accumulate a lot of that rain runoff, and that can cause the pH in the water to drop, which can lead to the death of fish and other organisms that live in those lakes. So that's a problem. They also have a lack of limestone. Limestone can act as a buffer against the change in pH. And it can also kill trees. And I'm not sure if this slide is supposed to say Clear Air Act or Clean Air Act, but regardless, there were some amendments made to an act in 1990 that targeted acid rain by forcing utilities, power companies and such, to lower their sulfur dioxide emissions gradually over time. And as the concentration on our y-axis here has decreased over time, our x-axis, the SO2 concentration has gone down over time, which is great. And so we're starting to see less and less acid rain because of that legislation. And that'll do it for Chapter 17, unless anyone has questions. Alrighty.